Cool. Hey everyone. So you just built an app, a really cool app. Maybe you built this app, the ChiPy website, and now you want to deploy it. So what might you do first? Well, you might write a shell script. It's conceptually simple, even though Bash is kind of a crazy language. But there's a lot of problems with it. If your script crashes, nothing restarts it unless you code it. It's not scalable across multiple machines if you want to deploy multiple copies of your code. It's not isolated. You have to write installer scripts to install everything. Like logging is configured manually. You can't really log it very easily. There's just a lot of problems with writing a bash script or shell script. So you might do an init script or a systemd. This is more standard across Linux distributions. There's interfaces for logging and running commands, but you still have a lot of the problems if you want to scale your app up, run it on multiple machines. You have to deal with load balancing and networking. Your dependency packages are not isolated, so it might be hard to replicate that among different environments. You might use virtual environments in Supervisor. Supervisor solves the restartability problem, and a virtual environment at least keeps your Python packages kind of isolated, but it still has a lot of problems, the same problems we had before. Your operating system dependencies aren't isolated. Upgrades are difficult. You can't, all the networking and stuff has not worked out for you if you want to scale. So there's still problems. You can use virtual machines. You can bake all of your code, all of your operating system dependencies into a single virtual machine, and you can spin that up, and you got the isolation kind of figured out. But virtual machines are heavy. They consume a lot of CPU and RAM. They run like a separate version of the operating system on your machine, so you're kind of sharing resources. They're slow, they're usually pretty big, and it doesn't solve the networking problem, like the load balancing if you want to scale up and down. So Docker might be the way to go. Docker lets you bundle all your code into kind of a lightweight image, which is like a virtual machine, but it shares your operating system's kernel, so you're not duplicating all the resources you need like a virtual machine would do. It's very lightweight. You can build it once and deploy it anywhere, which is really nice, but there's no automated way to do that deployment by default. You have to come up with your own solution for that. If you want to scale the networking, you have to work that all out. It's got a lot of the same problems. So this leads us to the topic of this talk, Kubernetes. So that solves a lot of those problems, the isolation, the deployment, the networking, the scaling. It uses Docker containers by default. So it solves a lot of the problems. The downside is it's kind of complicated, and it can be kind of expensive depending on how much fault tolerance you can accept. So this talk is shipping ChiPy, running ChiPy on Kubernetes. I'm Joe Jasinski. I've been working with Python for about 15 years and with Kubernetes for about 6. And so I'm going to talk a little bit about using the ChiPy website, an open source project that we host, as a test bed or just an example of how you could run an app, a Python app, inside of a Kubernetes cluster. Just to give a caveat, I don't recommend necessarily doing this because it's you could probably get a Kubernetes cluster running for about $50 at minimum, maybe $30 depending on the hosting platform. But this is to kind of demonstrate how you would make a small to medium-sized website work with Kubernetes. And Kubernetes is great for anything from medium-sized to large cluster sizes. So the objective of this talk is to learn the basics of Kubernetes. We're going to learn about the Kubernetes primitives like pods and jobs and deployments, a little bit about how to configure Kubernetes with your apps. We're going to run a local development cluster. We're going to talk a little bit about Helm, and we're going to discuss some deployment options. I kind of realized as I was preparing for this talk, there's a lot of stuff to cover. So I'm going to I might be rushing through it a little bit as much as I can, but hopefully if you have questions, just let me know. I'd like to clarify those concepts. So what is Kubernetes, also called KAS for short? It helps you automate and deploy your applications. Container orchestrator created by Google. It's maintained by an offshoot of the Linux Foundation called the CMCF, or the Cloud Native Computing Foundation, and they are like stewards for the source code and the trademark, and they hold the major conference for Kubernetes. So Kubernetes lets you manage running Docker containers and virtual machines now on multiple machines. If a machine fails, make sure that your workloads are resilient to that. You can reschedule work on different places so you never have downtime. You can scale up and down, so you only use the amount of resources you need, and you only pay for the amount of resources you need. Also, it lets you kind of abstract away your application from the deployment platform. So the nice thing about this is if you're developing an application for AWS, if you code it and you're not using AWS specific tools, you can take that application written for Kubernetes and move it to some other platform. And for the most part, you can get it to work. So Kubernetes gives you those tools to make it easy to do that lift and shift so you can prevent vendor lock-in. And that's pretty industry standard. For example, like it's one of the most popular GitHub projects with 107,000 stars, a lot of forks. They also have an annual conference in the United States, and actually ones across the world with about 13,000 total registered. 7,000 of those are in-person attendees, but they have ones in Europe, and I think, I forgot the other place. There's conferences all around the world with about similar attendance. Lots and lots of sponsors, so big companies are invested in it. You go to KubeCon, you see Microsoft and Google and NVIDIA, and IBM, all the big players. But we can't talk about Kubernetes without first talking a little bit about Docker. Docker is like the technology that kind of makes it possible, or containers rather. Docker's let you bundle everything, as I mentioned before, all of your dependencies for your application into a single image. That makes your deployments extremely reproducible and isolated, and therefore lightweight. So there's two concepts with Docker you'll hear a lot. There's Docker images and Docker containers. Image is like the code bundled up into an object, and then a container is like a running instance of that image. So you can, if you think of it like a class and a class instance, an image would be the bundle of code itself, and the container would be the running instance of it. And so the typical deployment workflow for Docker would be you build an image like locally or on a build machine somewhere. You build one image, you push it up to a Docker registry like Docker Hub, and then you can run it on multiple machines. And when you run it, it's called the container. And if we zoom in on the build step a little bit, we have what's called a Docker file, which is basically a script that tells you exactly how to install all the dependencies for your project. So here, this Docker file, you can see at the top, there's it says from Python 3.9. That's like a base image that you can use, which has Python pre-installed. And from that base image, I'm going to install a bunch of operating system dependencies, set some environment variables, pip install a bunch of stuff, and then copy in the code base for the project you're working on, and then set the default command that will run to execute the application. In this case, this is the ChiPy website. Here's a closer look at that workflow. On the left side, there's the Docker file that you just saw. On the right is the command that you'd use to build the Docker image. It's basically Docker build, and then you give it a name or a tag, ChiPy-1. You give it the path to the Docker file, and then you give it the context directory, which is where the build is to take place. And then when you built it, you would push it up to the Docker registry, which is step 2 here. And so basically, when we're talking about Kubernetes, Kubernetes fits in step 3 of this diagram. So everything else is done outside of Kubernetes, but Kubernetes is what actually runs the built to Docker containers. So Kubernetes has a lot of concepts or primitives that we need to talk about, like to set the stage here a little bit of what they are. Primitive is being the core components of Kubernetes. So one is a node, and a node is just a machine, like a physical or a virtual machine. It could be a Raspberry Pi or a cloud instance or a machine underneath your desk. And nodes make up the cluster, and nodes, most importantly, are what you're built for. So you want to minimize the usage of nodes, which is what Kubernetes is great for, because you could add more and remove nodes from the cluster. So that's the thing you're trying to optimize, is you want to get the exact right number of nodes for your workload and no more. Pods are the things that actually run your application. They're the smallest unit of work that runs in a Kubernetes cluster. And the pods run inside of nodes. Pretty much everything in a Kubernetes cluster runs inside of a node, they run as pods. Pods are traditionally disposable. So if you delete a pod, it should be able to just recreate somewhere else. The idea is that it won't have any state. You can just destroy it and recreate it at will. So the stuff that runs inside of it shouldn't contain anything important that can't be restarted somewhere else. You can run multiple copies of the same pod for resiliency. So if we zoom in on a pod a little bit, a pod is basically one or more Docker containers. Your Docker container containing your application that you want to run, or someone else's Docker container that you're including in your cluster. Pods each have a unique IP address inside of the cluster, usually like a 10 dot or a 192.168. And that lets pods talk to each other across the Kubernetes cluster. Basically, it works out the networking so they can all communicate. And pods are kind of organized by deployments. A pod, you can create a pod, it will run if the node gets destroyed or if the pod runs out of memory or something happens and the pod crashes, nothing's gonna restart that pod by default. But that's where deployments come into play. Deployments basically say, I wanna run 3 copies of a given pod, and Kubernetes make that happen. And the deployment is the thing that tells Kubernetes to do that. And roughly speaking, you can consider a deployment kind of equivalent to your application. You want to run 3 copies of the ChiPy website, represented here by this red pod, for example. That's where a deployment will guarantee that will happen. If a node is destroyed, for example, like if something happens or someone unplugs it or whatever, then the pods that are running on it will move over to different nodes. Or if there's not enough space on those nodes, the infrastructure can potentially provision a new node to schedule those pods onto. So services are like names for your deployments. They're like an internal DNS name, essentially, that lets you load balance traffic from one pod to another, and that's kind of how they can refer to each other. So if you have a service called ChiPy, pods can just refer to that name, and let's say there's 2 pods running the ChiPy website inside of the cluster, then that service will load balance between those 2 pods, and you won't have to like individually talk to specific IP addresses. It's kind of like a layer of abstraction. So here's kind of like a visualization of that. You have this green pod on the left. Let's say it wants to talk to the red pods. All it needs to do is make a request to service A, or the red service. That service will redirect traffic to one or the other pod. Same thing if the yellow pod is trying to talk to green, or the green is trying to talk to the yellow. The service isn't like a physical thing, but it's more like a lookup for where any individual pod can talk to other pods. So sometimes like you want to run scheduled pods. Like most pods, you run them, if it's like for a web server or something like that, they're going to run persistently. But sometimes you just want to run something that's going to run for a brief period of time or a long period of time and then terminate. So that's where cron jobs and jobs come into play. So cron jobs will use the cron syntax to run like a pod on a schedule, and a job will just run pods as needed. If you create the job, it will run it as is. So those are kind of useful concepts for doing things like database migrations or one-time tools or something that needs to run on a regular schedule. And then daemon sets is a thing that runs one single pod on every node. So if you need metrics or logging on every single node, the daemon set will guarantee that one pod runs per node. As I mentioned, pods are traditionally like stateless, but sometimes as people start using Kubernetes more and more people want to actually run stateful workloads inside of Kubernetes. By a stateful workload, I mean something like a database, something like that where it's got actual physical data that you don't want to mess with. So stateful sets enable this so that there's some rules behind how pods are scaled up and down so that you can run databases inside of a Kubernetes cluster. Config maps are one way you can specify configurations, like through environment variables or files. These are basically like config files that your pods can use. We'll see. By the way, we're going to see examples of all these, so it'll make more sense when you look at it. And secrets, you might want to expose your pods to usernames and passwords like SSH keys or crypto keys and such. So secrets are used to store that kind of data. PVs and PVCs, persistent volumes. So Kubernetes can abstract away the whole idea of a file system, which is really cool. So when a pod spins up, it has like a local file system. You can write data to that local file system. But when that pod goes away, all that data is lost. But what a persistent volume does, it's a abstraction for some remote file system, like an NFS cluster or Samba or Lustre or Gluster, or any number of several dozen storage providers that can plug into Kubernetes and your apps don't have to know what the backend provider of storage is. It just needs to say, I need this amount of storage, and Kubernetes will provide it. Like, I need 10 gigabytes of storage. Kubernetes will work with some backend components to provision some storage from outside the cluster. Ingress is an important concept. This is a complicated diagram, I realize, but most applications want traffic to go into them. Like you make a request from your browser, you need some way to get that traffic into the cluster, and that's where ingress comes into play. So ingress is basically like a set of routing rules for routing traffic from, like, if you make a request to myapp.com/myapp, that request needs to make it into the cluster and route to specific pods, and through some sort of through a routing table essentially. So the ingress is what it basically does that. Kubernetes is pluggable in that respect as well. So you have something called an ingress controller, which implements the ingress rules. Your application just needs to define the routes that it needs, but the ingress controller implements them. And that could be something like the Nginx ingress, which uses the Nginx web server to do all of this routing for you. Your apps don't have to know about any of that. They just need to specify what the routes are, and the ingress controller will take care of it all. It's a complicated subject, but that's the gist of it. So here's an example. There's like a ton of ingress controller options just to show you. There's you have a lot of flexibility in this pluggable option. One other thing is Kubernetes namespace. If you have multiple teams working in the same cluster, you can install all of the resources in a particular namespace. So one team can have one namespace and another team can have a different namespace, and you can set different rules between teams. By default, there's one called kubesystem namespace. That's the namespace where all of the pods for Kubernetes itself runs. And then there's a default namespace. By default, if you create something in Kubernetes, it will go into that namespace. Kubernetes uses a few processes that are known as the control plane. These are the things that actually make all the stuff happen. That includes an API server, which everything routes through, an etcd service, which stores the state of the cluster, like the pod definitions, everything like that. A scheduler, which schedules pods onto nodes. A proxy and a kubelet, which are how the individual nodes know how to talk with the API server. And there's a number of other components. And this I'm just going to touch on real briefly, but you can make your own resources in Kubernetes. Like if you're an app developer, you can create something which is known as a custom resource, which lets you extend Kubernetes and create your own types of, like you could create something that spawns up a Spark cluster or something like that by creating a custom resource. And you can, this is just a means to define how to do that. So everything in Kubernetes from the application's perspective is configured with YAML. So here's some examples of these concepts I was just talking about, some snippets of how they would look inside of YAML definitions. These configurations are basically, whenever you want to do something in Kubernetes, you create a YAML document and you apply it to the cluster, and then the cluster will make that state that you defined in the YAML, will make it into reality. So these YAML documents roughly have kind of a standard setup. So everything has a version, so you can have like each resource type has a version. So you, over different Kubernetes versions, as you upgrade Kubernetes, they can individually increment the different types of resources. The kind here actually defines what type of resource we're talking about, like a pod or a deployment or a service or config map. There's some metadata section, which includes the name. The name is how it will be referred to in the cluster. There's a label section. These labels are like really important. Labels are kind of free-form labels that you can tag to every resource, and they're useful for things like linking different things together, which I'll show you, or for filtering. Show me all of the pods with this label. Also for costing, if you're trying to like calculate costs, you can use these labels to group your costing, and it's just used for a whole bunch of stuff. Annotations are another free-form field that you can put like documentation or additional configuration into these annotations. That they're just free-form text fields that you can add to your resource definitions. And then there's a body section for the resource. And a lot of resource types have a spec for the body. Some of them have a data body. The body is like where you actually define the rest of the resource itself. So here's some examples of a pod. So as you can see, it's got a name, it's got some labels, it's got a Docker image. So this pod runs one container. The container is called web, and it runs ChiPy v1, and it executes this command to start up inside the container to start up the ChiPy process, and it exposes port 8000 so that other things can talk to it on that port. You can set environment variables in your pods, so you can have name value pairs, like the Docker container inside of this pod will have access to this Postgres host and Postgres port environment variables, and it'll be able to use those inside of the pod. So config maps, which we talked about before, you can actually define your environment variables in config maps, and then reference that config map inside of your pod. So you can say, I want to create an environment variable called debug, and I want to get the value out of the settings config map out of the debug key. That way you can kind of separate the definition of your pod from the configuration a little bit. And similarly, you can use config maps to mount entire files into your pod. So this example, the config map contains like a multi-line string here, meeting types.json, and you can mount that into your pod using this syntax here, and then this volume mount section here lets you mount the meeting types.json under this config directory, and then your application can consume that as it needs. Services, we talked a little bit about services. As I said, they're kind of a way to name your pods, and like the name for the services here. One key thing about the service is that it defines a selector, and the selector says any pod that has a label app ChiPy web server, I'm gonna direct my traffic to a pod with that label on it, and any traffic that comes into port 80, I'm gonna target to port 8000 of the ChiPy web server. The service count, I won't get too deep into, but it's basically you can define an owner, like a Kubernetes user that owns the pod. This is useful for setting permissions and such. So deployments look something like this. Basically, you have this template here. Oops. This template is basically that whole pod specification we saw just a minute ago, lifted and shifted into this deployment here. You can use all the same fields as in the pod. And then you can set this replicate key up here to say, I want to run 2 copies of the template down below. So make sure that there's 2 copies of this pod somewhere in the cluster, make it happen. Kind of that's the gist of how the deployments look. So Kubernetes, just like Linux, has a bunch of different distributions. Kubernetes has standards. You can pretty much interact with a Kubernetes cluster the same way, but different providers implement Kubernetes differently so that you can run on their platform, like Google, which created it, AWS, Azure, Oracle, Alibaba, and many, many, many more. There's a bunch of people, a bunch of hosts that are implementing Kubernetes. We're not going to talk about that now, but we're going to talk about mini distributions. So these are little distributions that are kind of useful for debugging, for running on your laptop, running on a Raspberry Pi. These are really good for playing around with and for learning about Kubernetes, or if you want to deploy a very small cluster, like something that might go in a retail store server closet or something like that. You might use like a micro distribution like this. And the one we're going to talk about today is called Kind. And what's really nice about Kind, it's like super lightweight. You can get started running this with Kind by running kind create cluster. That will create a Kubernetes cluster on your local machine. It simulates nodes. It's a single binary install, so it's really easy to install. You can optionally give it a configuration file that looks like this. So you can just say something like, I want to run a 3-node cluster on my machine, and it will create a little cluster on your desktop. And the only dependency is Docker. It's really funny, actually, because your machine is running Docker. Docker is running a Kubernetes cluster inside of it, and then Kubernetes is running Docker instances inside of it. So it's like, turtles all the way down kind of situation. Here's a really complicated kind config file, which we're using for the ChiPy website for this example. You interact with Kubernetes using the kubectl command, or kubectl, or kubectl. Different people say it different ways. This is like a command line interface for talking to the Kubernetes API. And what's really nice about it, it has a pretty standard interface. So you can do Kubernetes get, describe, delete, create, edit these, and then give it a resource type and a resource name potentially. Like this, the way you do this is all the same no matter what type of resource is. In addition to doing these basic operations, you can do things like you can view the logs for a pod. You can enter into a pod. This is really cool. You could actually enter into a running pod inside of a cluster, run commands inside of it, just like you would SSHing into a machine of some sort. There's a really good quick reference on the Kubernetes website that has like a whole bunch of Kubernetes kubectl commands, so you don't have to memorize them all when you're first learning. You can go to this and use that as an example. But a few other things I want to call out. Those YAML manifests we saw before, you could do kubectl apply-f and pass it in a YAML manifest file, and it will create all of the resources defined inside of that manifest. You can connect to a cluster with a kubeconfig. So when you first create a cluster, usually the installer will generate this credential file called the kubeconfig for you. And this is how you authenticate with the cluster. And it's got things like a private key and certificates and a user, kind of an embedded username. This is something that the kubectl CLI or other tools will use to do the authentication. By default, it gets stored inside of a .kubeconfig directory inside of your home directory. And you can override that with a flag on the command line for kubectl or an environment variable. You'll interact with this file a lot when you're dealing with Kubernetes. And Helm, really quickly, Helm is a package manager for Kubernetes. If you're building an app, you don't want to necessarily individually apply all of these YAML files all at once. You want to create something that kind of can deploy as a unit, that like all the dependencies, all of the jobs and pods needed for a particular application. And Helm comes into play for that. It basically is a standard for creating like a bundle of resources that then you can share with people online. You could run locally, you could publish it to a Helm repository. And what's really cool about it is you can template these configuration files with Go templates. So that means like if you want to name your application something different, or if you have different passwords and such, you can override that with this templating. You basically can pass in variables to these Helm charts, which lets you customize your application on a per deploy basis. So this is a great little tool or great specification that you'll see used a lot in the Kubernetes ecosystem. So here, some standard files in the Helm chart. There's like a metadata file called the chart.yaml and a values.yaml, which the values.yaml lets you define variables that you can use throughout all of those templates. And then you can override those variables on the command line when you're deploying the Helm chart. So, and here's an example of this is like a deployment YAML that we saw before, but it's marked up with all sorts of like the template syntax. So you could say, I want to allow the user of this chart to pass in a different replica count for the deployment. So they could say, I want 3 replicas or 10 replicas or whatever. This is a very complicated topic, but it's using the Go language templates, the syntax for that, similar to Jinja for those of you who have used that. There's some command line arguments for interacting with Helm, mainly to install a Helm chart. You can install from a local directory or from a remote repository. When you're installing a Helm chart, you can override those variables in the values file by passing in a syntax like this, or you can specify a file that contains overrides with this -f flag. You can list Helm charts, you can show metadata, you can uninstall. And then I just want to comment, there's a bunch of free Helm charts available on Helm Artifact Hub. If there's like a service that you want to install on your cluster, chances are someone's created a Helm chart for it and published it on Artifact Hub. Like for example, I talked about the Nginx ingress. Here's one Helm chart you can install. So the ChiPy website, how does this relate? ChiPy runs on Heroku. It's built in Django. It uses Postgres, and we use S3 for uploading files and static media. So if we want to run the same thing on a Kubernetes, we have to have these considerations. We need a Kubernetes cluster. We need a Postgres database. We need a persistent volume for storing the media that's uploaded. For this, to demo how persistent volumes work, we're not going to use S3. We're just going to store it to the local to the volume. We need an ingress controller to route traffic into the cluster. Optionally, it'd be nice to have a way to collect metrics of like CPU and RAM usage for each of the pods and nodes. We need to run some jobs in the cluster, like a database migration and collect static, which are common commands you could run in a Django system to like create the database and copy the static files into a space served by the web. And we need a way to deploy. So we already talked about kind. We're going to use kind for our Kubernetes cluster. We're going to use Postgres for our database. Kubernetes has this concept called an operator. But Postgres is a complicated piece of software. If you want to deploy it in a high availability situation, you've got like a primary and a secondary node, and if the primary goes down, the secondary takes over. And that's not something that Kubernetes knows how to do. That's just, like Kubernetes has no knowledge about how to replicate Postgres. So instead, people implement Kubernetes operators for things like Postgres. So you can deploy this service in Kubernetes. It's basically a factory for creating Postgres databases. You say, hey, create me a Postgres database, have it replicated. I'm going to give you a custom resource definition that defines how the database is going to look. The Postgres operator says, okay, I know how to create databases. I'm going to create some pods and deployments and whatever I need, stateful sets, to create a Postgres running instance inside of the cluster. And then if there's a failure, the operator kicks in and says, oh, I know how to replicate, or I know how to cut over to the other node, and then make sure that there's a new primary pod that's spun up in its place. So the operator is kind of like a specialized engine that someone's created to manage running Postgres in a cluster. And then I talked about ingress controllers. We're going to use the Nginx ingress controller for routing traffic into the cluster. There's a tool called the Kubernetes metrics server, which is going to collect metrics about the CPU and memory usage of the pods and nodes, so you can get reliable metrics for things that are running in your node. And then the thing too about this metrics server, we're going to just use it for a very basic use case, but you can export these metrics to a tool called Prometheus, but basically a reporting app that lets you chart and alert on certain conditions, like if the CPU is too high or if there's any number of different metrics. You can pass those along downstream and use those. To deploy things on Kubernetes, there's lots of ways you can do this. Lots and lots of ways. This is just a few examples. We're going to use something called a helm file, which specifies a list of helm charts that we want to install. It's like, here's 20 helm charts. In one shot, I'm going to deploy all these helm charts all at once. This is kind of a neat tool. I haven't used it in production, but I used it when working on this site, and I've heard about it a lot. And so it's kind of a neat project. So now that I've gone through all of that, I know it's a lot. I was trying to cut it down, but it's really hard. Let's take a look at the cluster a little bit. So first of all, I just want to so there's kubectl get po. This is kind of a basic command to list the pods in your cluster. Can you see that, everyone? This will list the pods in the current namespace. I can get po-all. I can see all the pods running in the cluster. So here's the different namespaces in this particular cluster. This kube system is the one I mentioned that has all the system level stuff. And this ChiPy namespace is one that I created for installing all the ChiPy resources in. And then there's a namespace for Postgres, which it has these are pods that are running for the Postgres operator. And then this is the actual database that the operator created. So let's do a few more things, like you can get deploy. Actually, I should be using, brought this keyboard for a reason. I hate the Mac keyboards. All right, so you can see all of these things we're talking about. And if you want to see the full YAML that these resources were created with, you can do I want to get the config map. I could display the YAML document for all of these resources. So here's a config map. Let's see. Actually, let me find something that's a little bit more interesting. Let me take a look at the ChiPy web server pod. Get po-o YAML, and then I'm going to look at the Kubernetes pod itself here. So this is the YAML document that defines that pod. And there's a lot of stuff that Kubernetes added here, but there's a lot of stuff here that kind of that we defined ourselves. So here's the API version, the pod, the type, the name. These are the environment variables that are exposed in this Docker container. The Docker container itself, it should be yeah, like it's running this image, this ChiPy v1 Docker image. It's exposing this port and mounting some volumes here. This it's mounting a volume called ChiPy static, which comes from this persistent volume claim. So let's take a we could go inside this pod here. Let's do the control exec dash. We could take a look at the contents of the pod, or you go inside the pod and look at the operating system that's actually running in. So I'm going to run a bash shell inside of the pod. I'm in the pod right now. If I do a PS, I can see it's running the USG server, which is running the ChiPy.org website using USG. It executed a apt start, which then triggered off these USG processes. If I look at the environment variables, I could see all those environment variables that we set from the config maps in the pod spec. So like, here's the database password. It's okay, it's going to be destroyed after this talk anyway, and it's only on my machine, so who cares, you know. Yeah, you got a few minutes to hack, but good luck. I don't think it's actually available to you, honestly. So, so here I'm inside the pod. I can look around, I can do stuff, which is really useful for debugging, kind of a break the glass feature. Another really great tool, actually, is you want to see logs, like standard out logs for your pod. So when I kick it off, those UWSGI processes are going to generate a bunch of log output. And so I can look at the log output by using the kube control logs and then give it the pod name. The dash F is just to follow. So as new log activity comes in, it will print it. Now, it's not really much interesting in these logs right now. Like the beginning of the logs, you see like UWSGI startup prompts, but down here you see like regular requests and such.
Who's doing these requests?
I mean, this is from before when probably when I was, the timestamp is probably old, May 9th.
Oh.
What day is it? Today's the 10th? Yeah. So you can also describe a pod, which is really handy. So if describing is slightly, we'll show some more status information, kind of give you a summary page for that pod. So here, it contains a lot of the stuff we saw in the YAML document, but there's some additional stuff in here that's not in the YAML doc, but it kind of puts it in a little bit more consumable way. You can see like the IP address that the pod was assigned, you know, the Docker image that the pod was assigned, all these environment variables that were mounted in. You know, it kind of summarizes that YAML file a little bit. And what's really useful here, well, you can't see it now, it cleans it up after a while, but these events, like if there's a problem with the pod itself, like if Kubernetes couldn't schedule the pod for whatever reason, like there's not enough nodes to support it, this events list is like a common place where you look to see, like it's kind of a log output for why a pod might not start. So I have this cluster running right now. I wanted to create it live, but I was having there's too many unknown variables that I didn't want to take that risk. So I want to show you first, I want to show you like the pod itself, or like the cluster itself, like the website itself, and then I'll destroy it and recreate it if you want, if you have time. But so first of all, and just as another caveat too, the Mac networking is a little bit weird. When I originally created this demo, I did it on a Linux machine, and then the other day I ran it on my Mac, and I couldn't get the traffic into the virtual machine of the Mac. So I'm going to do a little bit of a cheat, but it's still good enough to kind of give you a sense of. I'm going to port forward into the cluster. So I'm going to say I want to I'm not going to use the ingress basically. All right. If I could type. So what I can do is I can port forward. So traffic on my local machine I can send to a particular service inside the cluster. I'm going to send it to the ChiPy service. Autocomplete's not set up on this machine too, which is kind of killing me. So I'm basically opening up a port on my local machine, and if I go to that local machine, I can get to the ChiPy website, which is running inside that cluster. Yeah, I don't have the meetings, but it's a proper instance of ChiPy. One thing to note here, I'm going to maybe just show you a little bit of, if we have time, I'm going to show you a little bit of the resources that define all of this. So I moved that. So here is the ChiPy website code that I use to deploy this. Let me see if I can. Is that big enough? It looks really big, but I know it's hard to see in the back sometimes. So in the ChiPy code, in the ChiPy code base, I created this like K8s directory, which contains, this is just on my local copy. It's not something, I could publish it so people can see it. But so at first I created an implementation of this website using just raw Kubernetes YAML, like no templating, no helm. Like you could define all of the hard code, everything you want on the ChiPy website using these YAML documents. I know it looks like a lot, but you slowly build up over time. You start simple and then you just kind of build it out. The secrets for the cluster, like these are all the environment variables and environment variables we need to run the site, and the secrets we need to run the site. The deployment, this includes like the mounts from the secret config map, or the secret and the config maps here. This is, so this is like the raw way of doing it, like, but most people are using something like Helm nowadays, which I also created an implementation of the site using Helm, which you could see it looks a lot different. There's all this template markup in here. Like I said before, this template markup it's used to render out that deployment file, so we're not having to hard code a bunch of stuff in there. And this values file defines all the potential overrides, as I mentioned before, and the defaults. So you can pass in, these variables and override them when you deploy deploy the Helm chart. So since we're a little low on time, I just want to, maybe I can publish this. I create a README. If you want to actually play around with this yourself, I kind of created a README of how to do this stuff, like how to, deploy a cluster like this, and I can publish this code. But before I do that, let me just, should have changed directory while I was here. So remember I told you about the kind cluster. Kind is like the distribution of Kubernetes. I can destroy that whole Kubernetes cluster by doing just one command, and it's kind. So I'm just destroying that whole cluster. And then while that's destroying, I can recreate the cluster. Remember, just kind create cluster, you just pass it in the config file, and oops, for some reason I didn't copy. Oh, I think I did Control C instead of Apple C. It's weird when you have like you're using a regular keyboard on a Mac. So here it's creating a 3-node cluster with running Kubernetes 1.25. It's like as I said, it's running as a Docker containers running on this machine.
Can you like run Docker PS and see the nodes?
Oh yeah, yep. It takes like maybe about a minute to spin this up. Are we good on? Or?
Yeah, keep going.
Okay.
You said something about going into it and running commands. So is that you get a shell prompt somehow?
Yeah. So like you can actually you could have 100 nodes or 1,000 nodes and pods running on those nodes, and you want to say I want to go into this specific pod. Like you say kubectl exec into that pod, and you can get into a bash prompt inside that pod no matter where it is. It's super magical. So here, if I go with Docker PS, you'll see these kind nodes. These are the 3 nodes that spun up. And if I do kubectl get node, I could see, like kubectl get node is like Kubernetes' way of seeing the nodes that are in the cluster. I can see it's got a control plane node and 2 worker nodes, and they're both ready. You can even get the IP address that's assigned to them. And so, okay, this is an empty cluster without ChiPy installed. There's nothing in the default namespace. If I take a look at the whole cluster, I see that kube system is the only thing that has some stuff running inside of it. And there's a storage. This is like a storage driver for allowing volumes. So now what's really cool is if I run helm file, so helm file, if we took a look at this helm file.yaml, this defines like all the external repositories, these Helm repositories for different Helm charts for like the Postgres operator, for the metric server, for the ingress, and then it defines Helm charts for my local machine, like the ChiPy Postgres, the ChiPy itself, or like, basically it's like a manifest for saying deploy all these Helm charts at once. Yeah.
Yeah. What's your opinion on customize versus helm?
Customize. So I haven't used Customize a ton, but I know I get the reason for it. Customize is another tool for like configuring like your YAML documents, so you don't have to hard code a bunch of stuff in it. What's nice about it is it lets you merge YAML documents together, so the author doesn't necessarily have to anticipate every single thing that you need to set as a variable. I kind of like Helm, but that's mostly because of preference, and also I just like the kind of the atomic nature of being able to deploy a full app at once and delete. And but Customize, I know people like it a lot too. So I guess maybe it's saying it's time to go. Let me do one more little demo, and then I'll. So here I'm doing Helm file sync. That's the command to install all those Helm charts. And it's basically going to go and install everything needed for ChiPy. There's a little command line GUI tool called K9S, which is really handy for viewing stuff in your cluster, so we could see. Yeah, this is like a nice little tool for interacting. You can see the YAML definitions for all your resources. You can shell into them with one command. You can see the logs for them. It's kind of handy. I've never used this tool, but I've started to get more used to it lately, because like I was a purist using the kubectl, but I kind of like this tool actually. The more I use it, so.
Can you use K9S if you're running your cluster like on AWS or something? Or is it
Yes.
Okay.
Basically, that uses that kube config, and that kube config has embedded in it to like an address to how to get to the cluster, and as long as that's set, it will use it, and you're fine. So right now it's installing a bunch of stuff. it's oh, one thing I forgot to do. So since this Docker image is on my local machine, I didn't actually, it's not hosted in the registry anywhere. I didn't push it up anywhere. So one nice thing that Kind has is the ability to sideload a Docker image into the running Kind cluster. So you could build it locally and then copy it into your cluster. And I have it documented in this, yeah, here it is, ChiPy or Kind load, and you give it the Docker file name. And this will make sure that actually, I think I have to be in the right directory. Well, while I'm doing this, does anyone have any questions? Yeah.
Do you do any OCI compatible images?
So, I mean, that's the standard spec for Docker. So, I mean, my understanding is Docker is our OCI images. Docker is just the first implementation of the OCI spec, not the only one. I use the term Docker because it kind of is the original. But there's a lot of other tools that now will build Docker images, like Podman and what's the other one? IMG. And there's a build kit. There's a number of tools that will build Docker images now, and I've been experimenting with some of them. But Docker works pretty well by itself. The only thing is it's kind of tied to a company, and that company, I'm not sure how well it's doing.
I can't run Docker at work. And Docker desktop anyways.
Yeah, so Podman, yeah, you could use Podman, or you could use.
Or Rancher desktop's pretty good too. You run Docker D and let it do all the management from its front.
It just says you can run Pod, man.
Well, I guess since we're at 9 o'clock, I don't want to, and since I'm having trouble copying and pasting again, any more questions? Well,
So, what service handles all the names so the pods can talk to each other?
So that's like literally called service resources, and basically what the service resources are doing is they're talking to all of the kubelets, like the agents that are running on all the nodes, and telling those agents where to find all the pods, and then those agents write IP table rules to like direct traffic around. So it's like Kubernetes is like doing a bunch of stuff with IP tables, and I think newer like IP tables isn't the only. Here we go again. It's doing a lot of magic in the networking side of things to route stuff. So this usually takes a minute. So, but basically, if this will copy the image in, and then that deployment will finish like you saw before. But that's why I wanted to show you it running before I destroyed it and tried to recreate it. So.
He was on the fence. You could definitely publish that guide, that readme that you wrote. Looks awesome.
Yeah, I'll throw it up on somewhere.
Yeah, it's just
To echo this, I've been working on Kubernetes for years, and I set up my own cluster, and I did effectively what Joe said. It took me 3 to 4 weeks to figure it out, and then the last week I needed Joe to help. So, incredible.
I feel like the ChiPy GitHub could post Joey's guide to Kubernetes. I feel like that would be a further use.
I could at least put a branch out there,
Yeah, really. So it's very dense if you're watching it first.
Yeah, as I was going through this talk, I was starting to realize that it's probably more than a 45-minute talk. So, sorry, thanks for sticking with me.
So, you look at this on like you're showing deployment and everything's set up and running. But then isn't there some like monitoring or that like it'll spin up new things as load goes up or something?
Yeah, so there's a few mechanisms that do that. One, so like there's something called part of the Kubernetes control plane called the controller manager, and it's basically like a service that's polling all the time for all the resources, or like a bunch of resources, like deployments. And if it sees like, oh, I see a specification for a deployment that requires 3 pods, but I only see 2 pods, then that controller manager will say, I need to like schedule a new pod. So that controller manager will say, like, We'll create a new spec for a new pod, and then the scheduler will look for a node to put that pod on. Now, if there's no space on the node, like any node, if there's no nodes available because they're all consumed, then what usually happens is something called an autoscaler kicks in, and that's usually a component that works with the underlying infrastructure, like your AWS cluster, Azure, or Google, and it works with Google's API. It's implementation specific. That says, okay, I'm getting kind of I need pressure from nodes that are being created that I can't satisfy, so provision me a new node, and then once that node boots up, then the scheduler will be able to put that node on that pod on that node. And similarly, if the workload goes away, if the pod gets destroyed, or then that autoscaler can say, oh, this node has no workloads on it, I'm going to delete it. And so you save money.
I'm listening. Not sure what's power.
Approximately how many YAML files did you have to write for this?
How many YAML files? Well, maybe a dozen or two. Like, they're not a ton of YAML files. Like, it looks like a lot. But that's mainly because I was like, okay, if I want to run the ChiPy website as is, what do I need to do? And so I created a bunch of things. A minimum viable product could have probably been a little bit lighter, but I just also wanted to have stuff to demo. So here I just kicked it off again. Now the ChiPy web servers is starting to spin up, and this collect static job just ran, and the migrate job ran. So we could take a look at copied static files into the web root, or created the database. These are Django things to create the database.
It's the pod that errored.
The pod that errored is the create super user, and that's because the database probably didn't exist yet. I didn't spend enough time to finesse it out, but it will reschedule and create the super user eventually.
What was that side load?
Right here, it created the super user there. I didn't put enough effort in to make it nice. But I did it on purpose so I could show you what an error looks like. All right, thanks everyone.